All right, welcome back to representing linear functions. Okay, so we want to represent linear functions in a bunch of different ways, and we've seen that in the first video. We can represent a linear function as a complete sentence, as a table of values, as a set of ordered pairs, as a linear equation, or as a graph. We're going to look at some examples of functions and ask one very crucial yes/no question. Is it linear? First time we're going to ask, is it linear, is with word problems. Well, here's three different sentences, and we need to ask ourselves if it's linear. I'll go first on the first one. A new computer costs us $600 up front. Then if you want any additional storage space, each new gigabyte of space costs $5. So if I want one more gigabyte of space, it's going to be $5 extra charge. If I want two more, it's $10. If I want three more, it's $15, and so on and so forth. Well, each new gigabyte of space costs $5. This is a constant change, or we could say a constant rate of change. Every time I add a gigabyte, I add exactly the same cost to the computer. That's linear. So our answer, yes, it is linear. I'd like you to look at questions 2 and 3, so pause the video now and answer yes or no. Go ahead. Okay, so welcome back. Here we go. The question is it yes or no? The first one, or question 2 that is no. The cell phone plan is not linear because the cost changes, right? At first it's $2, then it's $1, then it's 50 cents, then I guess the next text is 25 cents, and so on and so forth. Every single new text changes in costs, so there is not a constant rate of change. And the third one, well, this is kind of a tricky one. You could say yes and no, and I kind of put that in there for fun. For a certain portion, we have a constant rate of change, 70 kilometers per hour. Every time I drive an hour, it's 70 kilometers of driving. And then we have another constant rate of change of 93 kilometers per hour. But taken together, this is actually a changing rate of change. So it would be more precise to say that no, this is not linear. Next question, is it linear? This time looking at table of values. In the first case here, it is linear. If I add 1 to my x value, I add 3 to my y value. Again, add 1 and you get 3. Add 1, you get 3. Now I put a little trick in here, but it's not much of a trick. If I add 2, suddenly I'm adding 6. This seems to change, but it doesn't actually represent a change in the rate of change. You see, every time I add 1 to my x, I add 3 to my y. So 3y for every 1x would be my rate of change. But in the other case, 6y for every 2x, well, guess what? That reduces to 3 over 1. So in fact, my rate of change remains the same. So the answer for number 1 is yes. Why don't you pause the video right now and try the other two? Go ahead. Okay, welcome back. As it turns out, the second one is yes. The rate of change is $100 for every 5 hours. It just stays the same. Every time you work 5 hours, you get $100. Or every time you work 1 hour, you get $20. And the second and the final one is no, that is not linear. As I'm adding, say, 1 to x, well, my y value goes down 3. But elsewhere, say, from 0 to 1, I add 1. But my y value goes up 1. That's a big change. So the rate of change is not constant in question 3, so it's not linear. Okay, next question. Is it linear again? This time we're looking at a set of ordered pairs. Again, I just simply look to see, as I change my x values, do my y values change as well? So, adding 1 to my x value down below, oh look, my y value goes up 1. If I add another 1 to my x value, my y value again goes up 1. And so on and so forth. If you looked at all of the points, you see that every time you add 1 to your x value, you get 1 to your y value. So we can conclude that the answer is yes, this is linear. The rate of change remains the same. Why don't you try the other two? So go ahead and pause now. Okay, the other two are both yes and yes. The second one, you can see that clearly because as you add 1 to your x value, you will be taking away 2 from your y value. Third one's not as obvious. But here's the thing, there's only 2 points there. And connecting any 2 points together, well, that's always going to be with a straight line. So it has to be linear. Next, we're asking the same question. Is it linear? This time we're looking at, I'll look at the first one. It is linear, and the reason why this equation is linear is because there's just a plain Jane x and a plain Jane y. Each of the y and the x is multiplied by a constant number. And it doesn't change, and there's no x squares. There's nothing strange like a square root of x. There's no odd exponents or anything like that. Just a y times a number, an x times a number, and a third number, which is a constant term. Well, why don't you try the other three? Yes or no for all three of them. Pause now. Okay, and the answers are yes, no, and yes. Okay, and I'll just explain the third one. The reason why it's no is that we have an x squared term right there. And finally, we can ask the question, is it linear for a graph? And so this is actually from a Google search. I just grabbed an image from it. If you look up linear graph, you just get thousands and thousands of images, and all of these are linear. Well, what does linear really mean? It's just line R. In other words, is it a line or not? And look, it's a straight line, one after another, after another, after another, after another. Every one of these is a straight line, so every one of these is linear.